Thank you for joining us today. We're incredibly excited to welcome Emma Smith to the stage. Emma is an active CPython co-developer, member of the MyPy core team, and open source and packaging engineer at NVIDIA. From standardizing type info delivery with the PyType 5 format to landing the new standard library compression .std module via PEP 784, her work impacts nearly every developer writing Python today. She is also currently co-leading the highly anticipated Rust for CPython working group. Let's get right into it. Please welcome Emma Smith to the stage. Thank you, everyone.
Thank you. So today we're going to talk about Rust, but before that, a little bit about me. As mentioned, I'm a Python core developer. I'm also on the Python security response team. So we're going to be talking about some security things. This is the security track after all. And I'm the mother of an adorable cat you can see and a feisty hamster. And yeah, let's get started. So to start with, let's look at a motivating example. Hopefully people can see this code. Effectively, this is an abstraction of a common use case. You have some networking message that you get in, maybe it's an HTTP response or a request, and you want to feed that off to a thread. So we have a generator that's taking in messages. We have a function that is doing work on those messages. And then we're using a thread pool to submit work to each thread. And if we run this code, it will, do what you expect. Actually, maybe not. So it turns out that there's an issue here. And if we take a look at the code, at that last line, there's what's called a data race. I'll describe what a data race is soon, but effectively it is a bug in the implementation of Python which causes the crash that we saw. So to talk about that, we need to talk about what the C in CPython means. CPython has a lot of C code. This is an analysis of all of the code that's in the repository. And if you look at these two lines, there's actually over 1 million lines of C code in CPython. And C is great for Python. It makes a lot of sense why C was chosen to implement Python. It's fast. The decimal module is 12 to 80 times faster than the pure Python implementation. It's also very portable. It's often called the portable assembler. Python has been ported to many, many different platforms because C is so portable. And it's also great for compatibility because a lot of operating system APIs have a C interface. And so the OS module and things like that can talk to the operating system through the C language. But there's a part of C that I want to talk about more today, which is undefined behavior. And so let's start with talking about that data race we saw. And the C standard says that a data race occurs when the execution of a program contains a data race if it contains two conflicting actions in different threads, at least one of which is not atomic, and this results in undefined behavior. So a way to think about this is if you've ever worked on like a Google Doc and you and somebody else are editing it, if you both end up editing the same line, that's kind of like a data race where you get kind of jumbled up between the two of you. And this causes crashes like we saw. So what is undefined behavior? Because it's not just data races that cause undefined behavior. And the C standard also gives a definition of undefined behavior, and it's behavior upon use of a non-portable or erroneous program construct or of erroneous data for which this international standard imposes no requirements. What does that mean? So how I think about undefined behavior, it's an error in your code which may or may not be caught either at compile time or runtime. The effect of it is completely unknown. And so if you're lucky, the program will run correctly. If you're unlucky, the program may crash. You may also see corrupted or garbage data if you read from the wrong location in memory. And it also can lead to security vulnerabilities, like as bad as arbitrary code execution. And there's a long history of buffer overflows and things like that. And so there are a lot of downsides to undefined behavior. Spatial memory errors, buffer overflows, there's temporal memory errors. This is a use after free, where you free a piece of memory and then something else tries to use it, and that's a crash. And data races, as we saw. So this is a quote by Chris Latner, who's the creator of the Clang C compiler, so pretty knowledgeable about the C programming language. And Chris says that there is no reliable way to determine if a large C codebase contains undefined behavior. And that's kind of a problem, because if it can lead to crashes or security vulnerabilities, we don't want those lurking in our code. I want to take a brief detour to talk about some of the changes happening in CPython today. There are a lot of major changes happening in CPython. There's free threading, or removing the global interpreter lock. There's sub-interpreters, or having multiple interpreters run in the same process. And there's also the JIT. And all of these together mean, I want to say that these changes are important, and don't take this as a statement we shouldn't do them, because we should do them. I think it's important that Python becomes more performant in the future. But it also means that over the last year, over 500,000 lines of C code have been modified. And that's a lot of code to change. And some of it's generated, but a lot of it isn't. And this is an issue, because there's a research paper which found that if you look at large code bases, most vulnerabilities and bugs come from the newest code. And there's actually exponentially more vulnerabilities and bugs in new code. The unit of the bottom line there is days. And so taking a look, reviewing what we've just said, reviewing what we just said, it's more or less impossible to avoid undefined behavior completely in C. Undefined behavior can lead to bugs and security issues. Bugs and security issues tend to be in newer code. And finally, Python has a lot of new and recently changed C code. So you might be a little concerned. I also want to mention that there are a lot of mitigations you can do to try to avoid undefined behavior and crashes and security vulnerabilities. So let's take a look at those. You can increase code review. And we can't really do that in CPython, because we already have a bottleneck in reviewer time in the project. Python core devs are volunteers, and we only have so much time we can allocate to review. You can also fuzz projects, and we're already doing this. Python's part of OSS fuzz, and we run fuzzing in CI. So that can catch some bugs, but we're already doing it. And it does find bugs. So it's not going to help beyond what we're already doing. There's also sanitizers, which we are already doing. And these basically check your C code and insert runtime checks to see, are you doing a use after free? Are you, is there a data race in your code, et cetera? And so we already run address sanitizer, thread sanitizer, undefined behavior sanitizer in CI for every commit to catch these. And then finally, a more recent change is that we can analyze the code with LLMs and say, tell me all the bugs in this code. And it will tell you a number of them. But there are people already doing this. The core team and external researchers are already running analyses on Python, and on the security team, we see reports that are LLM assisted, and so we're already doing that. But it's not enough. And I think it's not enough because Sorry. Fuzzers, sanitizers, and LLMs only partially mitigate the undefined behavior, but don't prevent it. And I think it's important to point out that, we also have seen a 4x increase in the volume of security reports. This is a statistic from Seth, who's the Python security engineer in residence. And the other thing I wanted to mention is that all of these mitigations cause increased maintainer load. As we get all of these reports, we have to triage each one of them. And oftentimes they're complex, seek crashes or things like this where, it's not immediately clear what the problem is. And so it's a question of, to me, it's a question of, are we just going to keep seeing an increase in the time that we spend on this, or should we do something to prevent that? So that's kind of, sorry. So that's where Rust for CPython comes in. And the idea behind Rust for CPython is that the Rust programming language is a way to avoid undefined behavior. And it's a very effective one. So the project is a collaboration between Python core developers, the maintainers of the Pyo3 library, which is used for binding Rust code to Python, and also Python community members. So a little bit about Rust. Actually, show of hands, who here is familiar with Rust? Okay, the vast majority of people. Awesome. So Rust on its website says that Rust is a language empowering everyone to build reliable and efficient software. And reliability is really important. We have all of these changes happening, and we don't want to break users. And efficiency is also really important because people want Python to be fast. And so there's a number of benefits to adopting Rust. And the increased reliability in Rust largely comes from compile time correctness checks. You can express things in Rust to check that your program will be correct ahead of time. It also doesn't have spatial or temporal memory errors like buffer overflows and use after freeze, which can lead to crashes and vulnerabilities by default. Additionally, data races are impossible by default. And there's pretty broad platform support. Rust builds on over 120 platforms because they also support embedded platforms. And there's also really good C interoperability. You can define Rust functions that have a C ABI, and there are tools to automatically generate bindings to a C interface. And there's also really widespread community adoption of Rust. Pyo3 is very popular, and a lot of popular projects like Pydantic and many others already use Rust. And I think it's important to especially highlight that data races are impossible, because with the adoption of free threading, multiple threads executing Python code means that data races are more likely to occur. And so protecting against that becomes significantly more important. Rust is, however, not perfect. Nothing is. Python runs pretty much everywhere that's vaguely Unixy and Windows and a bunch of other platforms, WebAssembly, things like that. And it's possible that there are users that Rust does not work for. And part of the adoption of Rust would involve finding out who those users are and if we can make things work for them. Additionally, not all the core team knows Rust. There are a number of core team members who do. But we don't want to prevent anyone from contributing to Python because they don't know Rust. And we also can't rewrite a million lines of C code right away. Unfortunately, I am not a X developer. And Rust can still have memory errors and race conditions with unsafe. And so unsafe Rust is a mode which allows you to do a few extra things on top of Rust. And one of the more dangerous things is to dereference a raw pointer, but it also allows you to say things are unsafely declare that things are safe to pass between threads, things like this. And this is a screenshot of the Rustomnicon, which is a book about unsafe Rust. And they say that the reason that these are relegated to unsafe is because they have the potential to cause undefined behavior. And so you need to be very careful about when you use them. One of the advantages of Rust is that it cordons off the area that undefined behavior can happen. And so you can focus on what are the requirements of my unsafe function to be safe. And then you can write your code such that you ensure that that's the case. And so there's a really great blog post by the Android team that analyzed a comparison between C, C++, and Rust. The Android project adopted Rust a few years ago. And the quote says, "Our historical data for C and C++ shows a density of closer to 1,000 memory safety vulnerabilities per million lines of code." That's kind of a lot. Our Rust code is currently tracking at a density orders of magnitude lower, a more than 1,000x reduction. If you told me, hey, if you write things in this language, you see a 1,000x reduction in vulnerabilities, I'd say, sign me up. So it's really appealing for this reason. And it's not just that it's designed to be safe, but in experience of people who have deployed it, it is also safe and reduces vulnerabilities. So another interesting thing happened, though, and this is from the same blog post. They found that not only did Rust reduce the number of vulnerabilities, they also found that their engineers were more productive with it. And part of that, I think, comes to compile time checks and being able to be more confident in the code. And so you can see here, especially for very large changes, there is a significantly lower revision rate for Rust changes. So I want to talk a little bit about the proposal for Python 3.16. We're currently discussing introducing Rust in 3.16, and I want to emphasize this is a proposal. It's up to the steering council to decide whether it happens or not. I also want to emphasize that it will be experimental. We don't want to introduce Rust and then find out that, 1 million users are using it on a platform Rust doesn't work with. And so if that is the case, or if there's some other concern, we can always remove it. And this worked really well for the Linux kernel, where Rust was an experiment for a number of years. And this last fall, they declared that it was no longer an experiment. Another constraint is that Rust code needs to have a C fallback. And the reason for this is that if you don't have Rust installed, or if you don't have Rust available on your platform, we don't want you to be unable to run whatever module is implemented in Rust. So I want to briefly revisit concerns with Rust. The first is platform support. And the problem is, people may run Python on platforms Rust doesn't support. There are several that I'm aware of, but there are people who run Python on plenty of platforms we don't know about. And so the only way to tell is to put Rust in Python and see if people say, hey, this doesn't work for me. And so the hope is that users of Python will say, hey, I can't build Python with Rust. And then we can work with them to figure out a solution. The next concern is that not all of the core team knows Rust. And the solution to this one is we want to focus on parts of Python where the core team members are comfortable with using Rust. This is more or less how the Linux kernel has adopted Rust. It's not like a team came in and said, hey, we're re-implementing your thing in Rust, but they worked with the people already maintaining that code to have a Rust implementation or be compatible with it. Additionally, there's a million lines of C code. Should we port it all to Rust? Some would say yes, some would say no. There's a variety of opinions on this. And I think the best middle ground is to incrementally migrate code to Rust where it makes sense. And so for each part of Python where people propose introducing Rust, we take a look and see, does Rust provide enough benefit to justify migrating things to Rust? Additionally, this is a point, we posted a pre-pep a number of last fall, and one of the concerns that people raised is, well, you can still have memory issues in Rust. And so the solution to this is to be very careful about when we use unsafe Rust, be very clear about reviewing it and signaling that, and additionally use well-tested libraries. One of the libraries that I will talk about shortly is so well tested that Mozilla reported a bug report which turned out to be caused by errors in the CPUs that the users of Firefox were using. And so I think the other constraint that we want to add to what we put into Python 3.16 is to target a significant improvement. We don't want this to just be, let's introduce Rust. We want to provide benefits for users. And so in summary, in Python 3.16, which is released in October of 2027, we'll introduce a new private Rust API to implement a module. And that module will be the zlib module, which is used by zip files and many other things. And we're going to use the zlib rs crate. A crate is kind of like a package in Rust. And it's used by Firefox, UV, Cargo, and many, many other projects. And the implementation of zlib rs is actually significantly faster than zlib or zlibng. And so it will speed up every pip install or other compression with deflate that you're doing. And so the hope is that this will provide a pretty significant benefit to users while also providing increased safety. One of the things that we want to think about, one of the most obvious places to introduce Rust is where Python takes untrusted input. So let's talk about the future. So after 3.16, we're hopefully going to hear from people where Rust is not available or introducing Rust would be an issue, and then fix or mitigate those issues. And then another is to introduce Rust in more places. So I've talked to a number of people about various parts of Python that could be re-implemented in Rust. This includes the I/O stack, the JSON module, memory view, the parser, and all of these are hypothetical potentials. But it would allow, but these in particular often deal with untrusted input where security is significantly more important. Additionally, if once we figure out a good Rust API, we could stabilize an official Python Rust API. And this would be maybe a replacement or to be used with Pyo3. And this would allow users to write extensions in Rust using the same APIs we would use in Python. This is kind of controversial, sorry. This is kind of controversial, but I think also making Rust required to build Python would be great. And so, fingers crossed we can do this, but there's a lot of questions about whether it's feasible to do this and whether it would prevent people from building Python. So that's kind of the overview of Rust for CPython. We're going to be at the sprints if you would like to work with us on implementing the Rust API and maybe porting zlib. And we'll be in the CPython sprint room. QR code here leads to our website, which is currently very bare bones, but we'll hopefully add more in the future. Thank you. And I think we have time for questions, if people have questions.
There's a community project, I think it's called RustPy or RustPython.
Yes.
And I think its main quality is that it turned out to be much slower than CPython. So where does that leave you with the claim that Rust will make everything faster?
Sure. So I think, yeah, it's a great question. So RustPython is slower than CPython, and I think that's for a few reasons. One is that RustPython is, maintained by a handful of maintainers, and also has not had 30 years of optimization of its interpreter loop. And so I think what I would say to that is mostly it turns out writing a very efficient interpreter is a lot of work. And rewriting the core interpreter in Rust is one of the areas where I think it may make less sense, at least for a while, to introduce Rust for that reason. The main interpreter loop is a huge C file, and there's a lot of intricacy in how that works, and reproducing that or matching it is a significant undertaking. Yeah. Oh.
Hi. You referenced Chris Ladner earlier in your talk, and I was curious to hear what your thoughts are on their approach with modular Mojo and trying to have a Pythonic, more memory-safe language as well in that effort. Anything that we can learn from that effort over to what you guys are trying to do?
Yeah, it's an interesting question. I'll admit I haven't looked very closely at Mojo, so I don't know if there probably are learnings there, but it would definitely be worth looking into. Yeah, thank you.
No, it's not.
Okay. Okay. Guido looked at it and said, maybe not. Okay.
Thanks for the talk, Emma. So you mentioned modules that will be re-implemented in Rust will have C fallback, and we already have a situation in standard library that modules implemented in C have a pure Python fallback. Are we going to be in a forever state of fallback, like 2 levels of fallback to maintain for forever?
So I think my answer to that would be no, hopefully not. Part of the reason why I hope that we eventually make Rust required for the Python build is so that we can remove the C fallbacks. But I think there will probably be a period of time where we have 2 or 3 implementations of things. I think most of what we're looking at currently is largely implemented in C and doesn't have a Python fallback. But I think that's also a factor to consider when we're looking at different parts of Python to implement in Rust. Are we going to have to maintain 3 copies of this? So, yeah.
Yeah. Hey, I was also curious about the whole C fallback thing. So, as you said, like CPython is a volunteer project. It sounds pretty demotivating to write something in Rust and be excited about it and then also have to write a C fallback. So how are you going to ensure the quality of those C fallbacks?
So I think the idea is that most of what we're going to target already has C implementation. So the zlib module already written in C and has been for many, many years. And I think pretty much all of the existing implementations that I discussed also have C implementations already. So I think it's more of a question of how do we make sure the Rust code matches that? And there's a lot of techniques you can use, such as differential fuzzing, to ensure that those match.
Yeah, but so how does the GCC Rust or GCC RS project impact any of these plans?
Yeah, it's a really important part, actually. So there are some platforms that LLVM, Clang, or so Rust is built on LLVM, which is the code generation backend that Clang uses, and it doesn't support some platforms. And some of these are maybe older platforms that not many people use, but they're available. They're used by Debian or things like that. And there's a Rust backend for there's a GCC backend for Rust, which allows using GCC instead of LLVM to generate code for those platforms so that we can eventually support them. I think that's still a work in progress, but I think by the time that we would require Rust, that will be a mature solution.
Great talk. You had mentioned that Rust tends to have fewer bugs per line of code than the equivalent C. It also seems to me, though, that the process of rewriting could introduce additional bugs that weren't there before because the C code is battle tested. Is the goal for the rewrite to be like a function for function, line for line port of the existing logic, or like a true rewrite of let's do this as if the C had never existed? And if so, what's the impact on maintenance there?
Yeah, I think it'll be a module by module thing. It'll depend. So for zlib module, it'll probably mostly be line by line because though we're using a different library, so it might be different. So I think it'll depend, but I think there are techniques like property-based testing and differential fuzzing that can be used to compare two different implementations and ensure that they match for a wide variety of inputs, and that can be used to reduce the chance that we introduce bugs when we write things in Rust.